Wiki Session. Thank you for being here so late on Thursday. So we tried really hard and we thought really hard how we can make this last Wiki Session success and educational. So just 2 words before, we try to split this in half. So the first half hour we try to answer like most of the questions as good as we can, and then in the second half we prepared something which is maybe a little bit more entertaining and will well, not that the first half is not entertaining, but this will also maybe involve a little bit organizing. Okay, so then the first question, this one I will answer. So I just read it out loud. So in a centrosymmetric system, I can have a heavy impurity with on-site spin-orbit scattering potential. That would presumably be quadratic momentum. How does it affect the transition temperature, etc., etc.? So to answer this question, so just the first very quick review is like if you have a singlet single band superconductor, so then normally we know that there's this Anderson theorem, so for a non-magnetic impurity or general as time reversal is preserved, then not much happens to TC. But if you have magnetic impurities or if you have broken time reversal symmetry, then the reduction of TC behaves with a universal function, which is just this gamma function here. Tau is basically the strength of your scattering potential. So then, to answer this question here, if you have a singlet superconductor in a single band, then if your impurity is even under time reversal, then normally nothing happens. But if you have a net magnetic moment, so if it's odd under time reversal, then of course it will affect the transition temperature. And then to make connection with what Professor Achterberg told us in his lectures, there if we have these cases where we have this strong spin-orbit coupling and are in this limit that basically the superconductivity is such that it mixes singlet and triplet components, then one can show that even a non-magnetic impurity behaves effectively as a magnetic impurity and can also follow a universal function like this. Then if you're in a more complicated situation that you have multiple bands, then more or less everything is open and there's no universal thing, and it depends on intraband, intraband scattering ratios. But the main message here is really the zeroth order answer to the question is it depends if you break time reversal symmetry or not. So was that a satisfactory answer?
I think so. I think that's the essential point is for S-wave superconductors, you never really said S-wave, but for S-wave, that's the essential point. If the impurity breaks time reversal symmetry, then you'll get suppression of TC. If not, so you said that exactly right. For non-S-wave, it'll suppress TC.
Okay, then we will go to the next question.
Okay. So this question is related to Brisson's lecture. And the question is, in a two-band superconductor, probably the case where the interband pair diffusion term is weak, do Cooper pairs in the small gap band really exist, or are they proximity effect from the band with the more robust superconductivity? So I'm not sure I exactly understand the question, whether you mean if Cooper pairs really exist, but I'll at least try to answer what I did understand. And this is as follows. So as a simplest example, we can think of two-gap system with this self-consistent gap equation. So in the case, so I think this question is related to these two off-diagonal terms which create this proximity effect. And in the case, say, where there's zero and these are completely decoupled, then we can imagine a situation where this equation has a solution and this equation does not have a solution. And this is exactly, I think, what you see here in this orange curve. And then you have two different TCs. But then if you turn on you turn on these terms, say weakly, you immediately are going to get a solution in both, even if you lie here in this region below this TC that's defined by that equation, and sorry, above this TC that's defined by this equation, and below this TC here that's defined by that equation. And that whole region is what I would call a proximity effect, I think at least. And I hope that's enough.
Jean-Pascal.
Huh?
I think it's a question more for theorists and for experimentalists. So I believe, yeah, like you, I have a little bit, I don't exactly understand what the question means.
Okay, so I put it in Zuki, it said
sorry?
put it weekly, that's me. The question is...
You shouldn't say!
Zuki said, don't ask the question, now I don't have time to put it in.
Unmasked.
So my question is, in that region above the TC,
Yeah.
the lowest TC, can we really say that we have pairing in the small gap band, the electrons from that band when Cooper pairs and we are there? Or are we just imagining something that's coming, migrating from the band which has the higher gap? Like if you put gold next to lead, gold will become superconductor. Just because super pairs from lead will go into gold. But it's proximity in real space. Can we talk about proximity in reciprocal space?
The point that is within the same sample at the same place. For me, I mean, you can imagine a case which is even worse than that. Let's imagine that you have, as I said, you have no coupling M11 and M22 0, basically.
Yeah.
And you have only internal diffusion. And then, theoretically, you have also superconductivity.
Yeah, but then you don't have this picture anymore, right? When you
No,
have
but the point is that you will have, just with interband scattering, you will have superconductivity.
Yes.
And nothing which is inducing superconductivity, it's no other band to induce superconductivity. So you cannot speak of proximity effect in that case. And it's superconductivity, just with interband scattering.
And always it can be repulsive. Yeah, no, but I think...
But I would like to have the answer.
I don't know, probably Peter is a better person, but to me it's a semantic question, because the question is M12. Do you call it a proximity coupling or do you call it interband coupling?
No, I think that depends on the distance, relative distance, meaning the coherence length between the...
No, but
There is no difference. There is no
there's no real difference, right? I mean,
Yeah,
it's just, so...
Iris,
I mean, I would the proximity effect is the situation where you can induce superconductivity in something which would not be superconducting without the presence of the superconductor nearby, right? That's what you're thinking. So if I were to say that M11 were 0, right, then that's the analog. And then it would be a proximity effect. But otherwise, if they're in a more generic situation, then you have an M11, you have an M22, and it's not really the same thing. What?
Above the lowest.
There is only one TC if M12 is not 0.
Anytime you have any M12 infinitesimal, then you always have...
there is only one TC.
TC.
Right.
Yeah, but TC does not have
If M11 is 0, M22 is 0.
No.
And if M11 is 0, M22 is 0.
Yeah.
Okay. And only M21 and M12 are non-zero.
Right.
Then you know you can have also superconductivity. Sure.
You can have superconductivity, but I wouldn't call it a proximity effect.
Yeah.
So there's no proximity effect. There's no one which can induce in the other one. So how do you?
This is maybe a semantics, but that's the way I understand proximity effect.
The question is.
I mean, maybe the right way to think about it is to go back to the weakly coupled case, where we talk about, for example, a Josephson effect in momentum space, right? This is a similar kind of thing. I couple two systems together, and I think of it as being a real space phenomenon, but I can describe it in momentum space as well. So there is some kind of an analog going back and forth, but in that particular case, proximity effect, I think of it as being slightly different. But, okay. If you want to call the existence of a finite M12 a proximity effect,
Yeah,
You're right.
But look, the point is, in real proximity effect, you look at spatially decaying something. That to me would define a proximity effect. Here we couple two Fermi surfaces, nothing decays on the other Fermi surface. I have a well-defined order parameter. So to me that is different from proximity effect, but again, if you want to call anything with non-zero M12 proximity, you know, we'll just speak another language and we'll agree on that on the dictionary.
This is interband tunneling.
Yeah.
So you write the dictionary from your language to Jean-Pascal's language to my language. Okay.
Shall we move on? I mean, it's nice to see that you have the same controversial discussion that we had when we discussed questions.
And it's all Ricardo's fault.
I'm sorry. It's all Snoop's fault. She didn't let me.
Yeah, we could have had this discussion 2 days ago.
Okay.
This question is also related to Professor Winston's talk. So the question is you mentioned that people try to really calculate the pseudo-Coulomb potential mu star. How is that done? So we can start from the screen the Coulomb interactions V and define this quantity. It's density of space times screen the Coulomb interaction average over the Fermi surface. And in a free electron gas, this screen Coulomb interaction can be calculated with Bayer Coulomb interaction divided by the electron gas dielectric constant, which can be approximated from the Thomas Fermi approximation. And then the Coulomb pseudo potential will be this formula under some approximation. And here the coefficient is not actually really matters parameters, because there's a log term here. Usually in calculation you choose 10 omega divided frequency, and this is characteristic electron energy. But now the real question is how do we calculate the mu or the equivalent to the screen Coulomb interaction from the first principles. You can go to these two references. The title is an initial theory of superconductivity. There are two parts. The first part is introduce a theory. The second part is apply the calculation algorithm to some real materials. It's not just a free electron gas. And the major point is they treat the electron gas, and they also introduced the other quantity called the nuclear density matrix, which is ignored in the traditional DFT calculation. And then they can calculate the superconductivity. Also, they include the strong coupling and Ashbrook theory. Then they found the superconductivity in real materials. So this is how they calculate the screen Coulomb direction or the Coulomb potential mu star. I hope that answers your question.
Sort of.
But we can't measure it. Right? I mean,
TC is very sensitive to this now, so this is usually the most difficult. I think we see it from excitation. It was only for very simple systems.
So the next question is for Jörg Schmaler. You mentioned that the Fermi velocity divergence flows to the ground point. This should introduce a curvature to the dispersion, given its negative effective mix. Does that affect the system in any way? I have in mind that Zhang said about the F-unit transition when the direct storm changes size. So in this question there are several things mixed up. There is a difference between effective mass and gap mass, which is relativistic mass in graphene. So effective mass in definition band mass is just curvature of the energy versus momentum. And when the renormalization of velocity takes place in graphene, if we consider that coupling is small and we can rely on energy, then the velocity at zero, close to zero momentum diverges, and therefore the spectrum of just gets curvature. So you don't get you get some curvature, and therefore the effective mass might be negative. but there's it's normal in band in semiconductors. So there's curved bands, and you get negative effective mass. It doesn't really say. It's not really important because the important mass for this transition. It's not really a transition. It's an interface between negative and positive masses. And for this, you need a relativistic mass, a gap which opens in graphene. The gap which is 2m. And then you can have this topological structure between with a different interference of between material with negative mass and with positive mass. They have different Chern numbers, and therefore in the interface you get a topological state which is protected. It's like a soliton, and therefore you have like in the here at 0 you have this king, and this is the chiral edge state, which is you get in topological insulators, and in graphene if there are two, like if the spin orbit interactions were strong enough in graphene, so graphene would also be topological insulator. But so if you have questions. So the next question.
So what is your question?
You have to answer it.
I forgot the question. No, actually, my question is I forgot the question. Could you repeat the question?
So the question is that will it influence the system that with negative effective curvature? It won't influence the system because this effective mass doesn't influence the relativistic mass mass does influence.
So in graphene we have two cones, right? Right?
Yes.
So we grab them all. There was a Fermi double.
No, you always have this. You have the one cone.
You won't have even number of states still, right? No, in the edge.
The idea, I believe, is that topological state, if the gap is large enough, occurs between the two cones. So you get somewhere between the two cones to get the band.
The edge state.
I'm just counting
the edge state.
Yeah, counting because it's Dirac, and then that we have all seen, right?
Yeah, no, but the Dirac cone that Zhang was talking about won't be that Dirac cone.
No, I understand that. The equation is not the same. It goes down. You need to, that's the reason why you need to break it down in this k-squared term, so to curve.
I really don't understand your point.
What's the question?
No,
if there is mass gap, so it will be topological.
Let's postpone this discussion.
Yeah, because symmetry
to the beach.
And parity is not broken. But you need for topological parity.
It's really like atomic. At some point we have to clap people.
Yeah. Here is a chemical question. Is there an iron superconductor which can be dumped until 1 pole per iron, which would be in a defined configuration? So I will answer just for 1 to 2 family. So baron and 2 arsenic 2. I don't know if we can dump with hole on the iron side, but we can dump on the baron side with potassium. So if we go to the end of the phase diagram, this phase is there will be this phase diagram with here potassium around 2 arsenic 2. And to speak about physics, this is not 1 pole per iron because there is just 1 pole per potassium and there is 2 iron. So there is just a half pole per iron. And this compound is a superconductor with a TC around 4K. and this compound was made, and they saw an effective mass sufficiently heavy, and maybe black nodes in the superconducting. Okay. So if we want to dot iron with ore, we also can dot ICAM. So we will dot with iron with manganese. And then if we want to have D5 configuration, then we have to go to the baron manganese 2 R72, which is antiferromagnetic, out of plane, and which have near temperature at 600 Kelvin with a very huge moment on the manganese. Here is the answer.
So you can do all the exercises on the knees, then
yeah, you didn't stress the joke.
Thanks.
So maybe we read the question.
Well, okay, so this is basically someone who has a whole feature.
Wait, what did you say?
So this is about how is it we directly draw or measure this. When the explain isolated fluid is in the BCS superconducting phase with 1-0 gap angle in phase coherence, are there any analogs of the Meissner effect and zero resistance? If so, what are they and can they be experimentally observed? Well, I mean, yeah, so like I was saying, this is about how you can measure or directly probe this whole, exploring BC or Bose-Einstein condensed state. And no, well, I mean, pretty much there are two, okay, generically there are two kind of distinct concepts which we should highlight. So the first is, I mean, BC does not mean superfluidity, right? So, I mean, ideal Bose gas is not superfluid, okay? So, therefore, in principle, there are different kind of, experimental signatures which you would like to see if you want to probe BC directly, right? Or superfluidity. BC is probably easy because of, because these things, these excitons, well, they recombine, right? So they have, they emit photons, and for example, if you have surface, right, of the, like, here, and then some here there are excitons, right, which presumably BC, then, if they are condensed, then the photons which, appear after combination are going to come out perpendicular, pretty much, right? So more precisely, if I, for example, start computing, right, numerically, the angle distribution of the radiation emitted from the surface, right, then as I put more and more excitons in my system, so as I make the state more and more classical, so BC becomes really macroscopic, then in principle I should see sharper and sharper angle distribution. So this intensity is steady, and I should see some places, right, which become sharper and sharper, right? And this steady is a normal, this is steady, right? So then you could probe the energy distribution of the photons, which should follow Bose-Einstein distribution function, right? I mean, with the specifying temperature involved. So in principle, you see, so those are the things which you would use to probe kind of single, kind of non-interactive BC. Now, when there are interactions, even in this regime, right? Then you would expect there's some, kind of supercurrent of some kind involved, right? And which is indeed supercurrent because of interactions, right? Between excitons. Now, the problem is that those things are neutral, right? So we don't couple to electric field, right? And as we discussed, there's no, as was pointed out, there's no mass transfer, right? So, like you would expect in the usual, let's say, helium, right? Strictly helium. Therefore, there are other more exotic proposals of how is it, what kind of supercurrent to expect, and how to detect in interference experiments, for instance. And And well, so many people talk, for instance, about the, and I think it was also mentioned somewhere here in the lecture today. They talk about the binary systems, right? So when one can separate charges. So this is whole type, and this is, for example, electron type layer, right? So which is if they're close enough, 10 nanometers, something like that. Then the Coulomb interaction will be strong enough to bind to an electron. So I could schematically do it like this. And in principle, well, I mean, since there's going to be charge imbalance, right, it's going to be a electrodipole moment. Now, then one needs to, well, there is a proposal by Jan Zajanik, actually, very recently, this year, I think, which amounts to essentially deriving the supercurrent density in this system, closely analogous to the spin current density, but here it is the current of dipole. Since here we have kind of a label, right, which is a dipole, we can couple to electromagnetic field, and since the constituents of the lexicon here is still a charge, then, well, okay, this is minus E, this is plus E, then what would happen is that the current turns out to be proportional to the applied magnetic field, but in a parity breaking setup, so it's D plus E. So if I apply magnetic field somewhere here, well, I will have a current proportional to cross product. Now, well, then in principle, now what they, or at least we can theoretically show, right, that if now you bend this double layer in a cylindrical geometry and make this current circulate around, then the flux through this area, or in the cylindrical setting like this, should be compressed. So the flux is going to be equal to some fraction times the flux number, or flux quantum, which is 2 pi h over E. And the entire magnetic susceptibility of this system, which is pi to rho, because these are two quantum velocities, this is substrate, right? So that is the proposal. Now, if this was measured, I guess not. But it's the closest thing. Otherwise, you could speculate. There are probably many ways to speculate about this, but I don't think there's any kind of indication.
Pretty good marks. Yeah. Thank you for giving my tomorrow morning's lecture.
Look,
No. Hey, you saved me time. Thank you. Good.
So you have not the excuse to say that you're going to run out of time, right?
That's right.
That saved at least 3 slides.
Wow. Okay.
Okay, so now we come to the second.
Wait, as an organizer, let me postpone the inevitable. Yvonne, wasn't there a question you postponed from last Wiki session to this one?
There was actually. I think the question was also in the graphing system, on the ultra-fast time scale, they see the population inversion, and the question they were asking, could you have the electrons and the holes both condensing?
That was actually, you didn't ask that question,
No. we got
I asked it, and because I asked it, I think they can.
But we decided to.
Martin is not here anymore.
But we decided to postpone it because Peter would be here, right?
Okay, so the point is that what happens is that if I remember correctly, the time scale in which, so the interaction term does not allow a thermalization of, say you create some population inversion like this, then it's stable because the interaction term does not allow thermalization from this to this state, and you need phononic processes that have a longer time scale in order to thermalize the system. And in these time scales, I think that exactly on the same lines, you can create pairs like excitons, and I don't see why not.
No, one needs to think about the magic sounds that are cool, because I mean,
but that's exactly what Schmalling did think about.
I think I'm going to turn over my lecture to these guys.
Otherwise, but look, what is the time scale there, right?
No, I'm not going to talk about graphing, but I will talk about the answer to that question in general. Yeah, I mean, indeed. So one of the points you're saying about the need for a superfluid in these models is that you have separate conservation of electrons and holes. If you don't have separate conservations of electrons and holes, then actually you have generically gapped spectra, no superfluid-like behavior. And of course, the single particle term is ruled out because it's a cone, and the pair term here can only happen if there's recombination emitted by a photon. And to the extent that's slow and on that short time scale, yeah, you can have a condensate. Has anybody seen it?
All right, now we're out of excuses. We're out of excuses.
I will defer. Marino will be our speaker here.
Sorry?
Marino will be our speaker for the question.
Yeah, okay. That's good. Good idea, yeah.
So the point is, we have how do you structure? We start from the
Let's start from the question.
Yeah, but I think the following. Okay. So we organize some questions which are supposed to be sometimes physics related, sometimes physicists related, and it's basically the organizers compete for a prize. And so we will basically have points. We'll have points here.
No questions.
And it's really easy. So who has the most points wins. So
can I ask a question without points?
The pointless question? Yes.
1 point.
The answer should have been no, you do not get any points.
So do we get 2 points because he's not getting in?
Okay, let's start.
But there is a fourth one.
There's Marino.
Marino. And Marino.
Marino is fine.
So
but we cannot. Okay.
He will be represented.
Yeah, he will show up at some point.
We all might end up with negative points, and then
Okay. Then you Okay.
So in this questionnaire, right? I mean which we
satisfactory.
I mean, do they have buzzers?
this questionnaire, it was, the question whether we are satisfied with the wireless. And I mean, there was an unsatisfied column, and it was set, printed there, yes. So is it kind of
suggested?
No.
The answer is no. We're not satisfied with the wireless.
Yeah, but was it so obvious or not? Is it not printed there?
Okay, so then it's but it's clear how it works. Okay? So you're supposed to. Okay. That's the warm-up
Okay, so let's narrow it down.
Multimeter and a series of.
You rule yourself out because of being an experiment.
No, that's no excuse.
No, I gave the answer. Give me a set of resistors and a multimeter and I'll know it.
Infinite set.
Yeah, infinite set.
Here they are.
Never mind, you can classify yourself as
4 is enough.
Actually, you only need like 700. You can simulate us.
Or in other words, guess.
I'm going to get this on a special high key.
Okay, so Peter says B.
Peter says B.
I don't have your
I'll say B. I like to overpower.
There is no square root of 3.
I remember that this was in physics today, one day, and I googled the answer and I forgot.
Alright, you forget.
Yeah, but there was a logarithm involved in the full answer.
Oh, no, the answer is there.
Yeah. So both guessed B.
Yeah.
I'll guess C because C is more than B.
So the answer was
It's too late. I've already voted.
The
for
answer
B.
is D.
Do I get a point because I'm closer to B?
What was the answer?
D.
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 So you are the 3 of
We already have one. Yeah.
Okay, so here's the second question. You wanna?
yeah. Here is a review of Mazen. And there is a very big beginning of the.
Victor,
I know 6.
Yeah, I also know 6. I know 6 as well.
Everybody knows 6.
But I guess you can get more than one.
So we will guess for the final one.
Do we have to fill in the in numerical order according to Mazen, or?
So the honest answer is no. Oh no, yes, because we are not able to otherwise open these things.
So, hey, I want to go around and videotape you guys. How do I videotape you guys?
Do whatever you want.
Okay, how do I get this off?
No, it'll die.
Oh, okay.
That's the problem. The battery's dead.
Oh, unfortunately.
Okay,
so
6 is never trust the theorists.
Yeah,
that we know. 1 is stay away from oxygen, I
so
think.
we start,
Yeah, 1 was stay away from oxygen.
One is stay away from oxygen.
Say hello, Elia.
Okay.
So there was a
one is stay away from oxygen. So anybody knows which we first collect the answers, then open up.
Stay away from
What else?
Now you can hide the picture.
Yeah, stay away from. There was a stay away from magnetism.
But come on, this was.
Okay, so yeah.
Stay away from magnetism.
Stay away from magnetism.
The electrons?
Yeah, there was something about the electrons.
Okay, I guess it's something like this. What you said, the electrons?
He repeats everything I say.
Electron
Nothing that can look like that.
How about this?
Even if
Don't.
you put a wall side.
I think better buzz us.
Once I heard you say that you
Sure. I want to use my phone to a friend.
Oh, you want? Okay.
You should include the audience here.
I want to phone my friend Rosé Valin. Hello, Rosé.
I think there is one.
I'm on this television show.
High symmetry is so it's about symmetry. There is one symmetry.
So shall we open another one
for audience?
No, I get that one. That's my friend.
Okay, so should we do so?
That's the first one. The first one. That is the first one.
Okay, the first one.
This is seriously embarrassing.
Highest.
Ah, okay.
Cubic symmetry is the best I
Okay, so then.
Okay, so the oxygen magnetism.
Let's just open it.
Oh, that, yeah, okay. Is that a room?
Sorry, guys.
Yeah.
And then the last one is
See, I told you stay away from insulators.
So there is two for the audience. Rosé.
Yeah.
He said insulators. Yeah. I decided not to repeat because Peter might have complained.
Oh boy.
Okay, so here's the next question. So we've heard a lot about neckties and orbitals, and since the title is multi-orbital.
Too many.
Okay.
My answer is too many.
Okay, you can choose between the answers. Okay.
Hey, I have a question. Which model?
Which model? Yeah, that sounds around.
We said, okay, roughly, it's a 10 orbital model.
No, but that changes not
Yeah, so they're all the same order of magnitude except the first one.
Semi-physics.
D. I say D.
Highest symmetry possible.
I say between A and B.
Okay,
C.
Yes.
But if they're all degenerate.
I said D already. I can't get out of
I
it.
did D. Okay, so D, D, and C. Okay, so then.
It's D or
Okay, so.
it's a D or a
So we took this paper. It's a very early one by serious people. And they, in the conclusion, they derive several, and then in the conclusion, they say the following. So the minimum number is 27, or if you want to go for the normal 1 to 2s, or beyond 40.
Okay.
So I guess C and D is.
Okay.
So everybody gets a point.
I was in the back of the bus. I couldn't see.
A busload. A busload is the correct answer.
Elias, say hello.
I know, I heard the story. I had to move that on.
So I was saying, if they put in oscillation mode, 5 plus 5.
Actually, 6.
12. Hello, everybody. 12. Hello, everybody.
6.
Oh, no. So, I guess we
You should count now.
Yes.
We should 6, because the other one now
No, but the others are willing enough.
just watching.
How many of these are physicists in this one?
Actually, he might get.
How do we know those are physicists?
6 and 1 supervisor, yeah.
By the way, Johannes is also just.
Yeah, Alexander is not doing anything.
But I'm in full action here.
6. Okay.
But not all are physicists.
Yeah, that's what I was thinking too.
They have one was bus driver.
So this needs a little bit of explanation. So this is that's the last one, eh?
Yeah.
So each one should now like recognize a graph that he produced himself in a paper. Anywhere in his career. So we basically spend hours and hours searching the web for all this publication.
Do you have to give also the reference of the paper?
Well,
We'll bring the
Extra points.
Yeah, you just identify your.
yes, and don't be deceived by, points or experimentalists and lines or. Okay, so you can.
Yeah, I think you should bring on all of them.
Yes.
The last one is mine. The one on the left is mine. Lower left is mine.
By the way, this was the only figure we did not need to do anything.
Wait, I have to ask a question. Are there no access labels in that figure in the published form? My
Okay,
God.
so here's the last one.
I hope it's not.
Okay, then you can get an extra point if you say which year it is.
And you have to explain,
98.
Mine is 19.
No, okay, but so does anybody
Mine is the top, right?
The top right?
This?
Yeah, it's on Bisco 12212. It's the sunroof for the overdose sample and a thin film. And this is about the zero gap, and I'm not sure if it's the PRL 2002 or PRB 2005.
He's not sure. He's not sure.
Say the year for the extra point.
If it's the PRL, I think 2002.
Wait, 4 or 5, it's 2?
We'll check. You can just write it down. But yeah.
Okay, so 2002 you said. We have to remember.
Mine is 94.
94.
Oh, it's the optical connectivity of a D-wave superconductor.
I can give you maybe the cutoff frequency that I used to get this.
And what year is yours?
Mine is 98.
And what
It's PRB 98, and this would be the... Huh?
Are you sure that it's 98?
I mean...
So yours is the last one, right?
Sorry?
Yours is the last one?
Yeah, this is the last one. It actually might have appeared in more than one paper, but there was a conference proceedings where the same picture appeared.
Duplicate publication.
Yeah. Well, also I'm a little bit confused. I mean, you said there are tick marks on the axes, but there are no languages.
Yeah, there are no numbers.
I hope the caption was clear.
Yeah, so let's check.
Hey.
Yeah.
97.
Oh.
And yeah, that was 9.
So
That's what I get my extra point.
Oh, Ricardo.
So you get an extra point.
Yeah, I get an extra point.
Ilya, I have to ask, what is that a plot of?
This is the plot of the... let me think. This will be... The point is the paper is on Hall effect. So whether it's a Hall conductivity or the Hall angle, I need to remember now.
Negative points?
Yeah.
I like to think that you get away with this.
Okay, so this is then the end, and so we just want to take this opportunity to thank the organizers for this really great conference. And since, okay, Ilya and Peter both have the same point and Ricardo is close by, so we have this prize. And we just share it and drink it all together.
There was time for
I
the
would
West over
like
Europe.
to say thank you very much.
Yeah.
I have wanted to try Capcos since I got here and saw it in the supermarket, so we will have a chance to do this. And if there's anything left, who knows, we can have it after the close of the session tomorrow.
Yeah.
I don't know because I don't drink, so...
Ricardo, so I'm sorry, but France lost to the US.
The trash talking, the association trash talking interview.
Thank you.
Turn it off.
I'm going to turn it off now.
Yeah, turn it off.